Okay, if you're watching this video, it's because we're having a snow day. I'm just going to have you take some notes today. There won't be any assignment to go along with it, but I do want you to get these notes taken so we're ready to take up a little bit of this time when we come back. All right, this material goes along with section 4.1 in our textbook if you want any additional reference. Okay, so suppose that you have a function, and I want you to get nice and simple, 2x, and you have another function, x squared. I want you to note the language here is to use a lowercase f here and an uppercase f, and you've got to recognize that those represent two different functions here. If you take a look at the way these two functions are related to each other, I think you can see that the derivative of big F is little f. Those are the two functions that I have picked. Okay? When this is the case, when you have this situation, then we can say that big F is an antiderivative of little f. This big F and little f notation is sort of universal, so you have to get kind of comfortable with it. You can use some other variables as well, but this gets used a lot. There's some other antiderivatives. This doesn't say the antiderivative, it says an antiderivative, and that's because there's a lot of other antiderivatives of little f. But for example, look at g of x, and if you see that g prime of x is also an antiderivative of f of x, or consider h of x, and you can see here that h prime of x is also an antiderivative of f of x. So when we take derivatives, there's one answer, but when we take antiderivatives, there are going to be a lot of answers. Okay, these answers, if we take a look at this as the example, if f of x equals 2x, then the family, let's call it the family of antiderivatives can be shown by this function, f of x is equal to x squared plus different values, some kind of constant. So in the first antiderivative that I did up here at the beginning here, my antiderivative had a constant of 0, and then I gave another example with a constant of 3, another one with a constant of -5. Any constant will do, all right? This is called the constant of integration. That's a new word, integration. There are two different words for what we're doing. One is called antiderivative, and one is called integration. We're kind of go back and forth between those two words. Okay? So that's your basic idea. We learned how to take a derivative, take a function, find its derivative. We're now going to take a function and find its antiderivative. So let's take a look at a couple of situations. If I tell you that y prime is 3x squared, then a little bit of thought, I'm going to give you an actual process later on, a little bit of thought will tell you that y is going to be equal to x cubed. Can you see that the derivative of x cubed is 3x squared? And we put the plus c on the end to indicate or x cubed plus 7 or x cubed minus 8 or any other constant on the end. Okay? Another way of saying the same kind of thing is to say if the derivative of y with respect to x, dy dx is equal to 4, then what did y have to be? In other words, can you tell me a function whose derivative is 4? And again, a little thought will tell you that answer is 4x. And we know that this variable is an x because this notation tells us to use it. And then you put on the end of it plus c because it could also be 4x plus 2 or 4x minus 5. Okay? All right. We've got a lot of vocabulary here today. Differential equations. A derivative is simply another function. It's just a matter of what you call it. So you have to kind of get comfortable looking at y prime, the derivative, as a function. Another way of saying that is the derivative of some function is some other function. Okay? Or you'll sometimes see it this way. It's almost like multiplying both sides times dx. dy is f of x dx. These are all different notations that kind of say the same thing. I have a function that is the derivative of some other function. And your goal of going back and finding what y is called, the big word, so I have to stop talking when I write it down. Anti-differentiation. Anti-differentiation. There's another word for this. It's also called indefinite. The indefinite integral. It's two different kinds of language that can come out of this process, and we just have to be comfortable with both of them. Okay? So I'm going to give you some sort of generalities first, and then I'll get into some specific examples of how you make this work. Okay? If I give you this, the derivative of y is some function times dx, and you take the antiderivative of both sides, just like you would take the square root of both sides, and you would add 6 to both sides. The symbol looks like this. It's kind of a stretched S. That's the symbol. And it means take the antiderivative, take the definite integral of both sides. That's what it tells you to do. Okay? That's a new symbol for you. Just like this means take the square root, this means take the antiderivative, or take the definite integral, indefinite integral. Excuse me. All right? And when you do this, when you take the indefinite integral here, you're going to get y. And when you take the indefinite integral here, you're going to get some other function. Okay? We're going to put a plus c on there to indicate that we know that it could have a constant on the end and it would still work. And this function right here is the derivative of the antiderivative. Okay? The derivative of the little function up there at the top. All right? That's one way that the notation is going to be written. I'm going to pause for just a second because my phone is ringing. Okay, sorry about that. And so I don't remember where I was. All right, the second way of telling somebody how these two things are related to each other is to say that if you take the derivative of the antiderivative, if you take the derivative of the antiderivative, it's going to just take you back to the original function. And just think about that for just a second. That's like saying if you take a function and add 3, and then you subtract 3, it's going to take you right back to x. If you take a function and multiply it by 2, and then divide it by 2, it's going to take you right back to what you started with. So that's just getting a handle on what this notation means. This says if you take the antiderivative, and then you take the derivative, it's going to take you right back to where you started. Okay? And there's two ways to write this. The way I've written it here. And the second way is to put that same information internally. I love it when there's lots of parentheses. This says if you take the derivative of a function, and then you take the antiderivative, that you're going to get right back to the original function. If the last thing you do is take the antiderivative, then there will be a plus c on it. If the last thing you do is take the derivative, there won't be, because a plus c will develop here. You'll get a plus c here, but the derivative of constant is 0, so you will not get a plus c on no plus c on this, because the last thing you took was the derivative. All right? This is a lot to take in. Okay, let's get down to the rules. What can we do, and how can we do it quickly without having to panic out? So first of all, remember that the derivative of a constant is 0. Okay, so therefore, over here, the antiderivative of 0 is a constant, any constant, okay? The derivative of a constant times x, the derivative of 2x is 2, the derivative of 3x is 3, the derivative of kx is k. Therefore, the antiderivative of a constant other than 0 is kx. It's going from one direction and going backwards. And over here, when you take antiderivatives, you have to put a c on it every single time you take antiderivatives. Okay? One of the things to note here is that this dx tells you what variable to use. So if I asked you to do the antiderivative of k dp, then the answer is going to be k times the variable p. This is telling you that the constant, the value of the variable that you're using. All right, now let's get to one that's a little bit more interesting. If you take the derivative of x raised to a power, remember this old rule, you can do it now without even thinking about it, okay? We need to think about how to make that go in reverse. If I have x to the n, and I want to go backwards. Now, if I had this, and I took the antiderivative of this creature, it would go back to x to the n. But if you're going to get to the antiderivative of x to the n, you just have to kind of back out of this a little bit. Over here, the power went down by 1. So over here, the power is going to go up by 1. Over here, you have to multiply. Over here, you're going to have to divide. And then put a plus c on the end. That is something that you need to memorize. This needs to be memorized. We'll do a couple of examples so that you can actually see that this really does work. Okay? So the rule says that it's x to the n plus 1, so that's to the 5. And then to take 1 over, not 1 over this, not this, but 1 over this, right here. Put your plus c on the end. When you do that, you can stop and just check and see that you're getting the right answer. This is just a check. What is the derivative of 1/5 x to the 5th? Or it's 1/5 times 5x to the 4th. These two cancel out, and you get x to the 4th. So that's where that division part comes in, to help cancel that piece out. Okay, just another one, just so you can see how it really does work if you pay really close attention. The negative exponent. The rule says you need to go up. The power needs to go up 1. So x to the negative 5, and then not 1 over negative 6, but 1 over negative 5 plus c. And in fact, you'll see the answer like this, or you'll see the answer this way. You'll see both answers, but this is the one that comes directly out of the formula. And once again, I'm just going to check it here, so you can see that if I take the derivative of negative 1/5 x to the negative 5, I can put the plus c in there, that's fine. Then I'm going to get x to the negative 6, you subtract 1. There's that negative 1/5 that's already there, and then I'm going to put the negative 5 right here. I did that kind of backwards. Let me do that again. That felt pretty awkward. Sorry. I'm going to put the negative 1/5, leave a little space, and I'm going to put negative 5 x to the negative 6. The derivative of constant is 0. These two cancel out again, and you get x to the negative 6. One more. The antiderivative of x to the 1/2, which works if the powers are fractions as well. So I'm going to follow the rule which says add 1, 1/2 plus 2/2 is 3/2. And then I need to do the reciprocal. I need to do 1 over 3/2, and that just means reciprocal. Okay, it just means reciprocal. So the reciprocal of 3/2 is 2/3. And then put your plus c on there. And last time for the check, if I take the derivative of 2/3 x to the 3/2 plus c, so 2/3 times 3 halves x to the 1 half. The derivative of a constant is 0. These two cancel out, and you get x to the 1 half. Okay? All right. We have another rule called the constant multiplier rule. If you have the derivative of a constant times a function, your answer is going to be a constant times the derivative of the function. We've used this rule over and over and over again. Likewise, if you have the antiderivative of a constant times a function, you can take the constant out and just do the antiderivative of the function. So this just makes life easier. So I've written on one of the things in the classroom, constant multipliers are your friend. They make life easier as long as you recognize them. So here's a function that has a constant in front of it. And you can just pull that 3 out. And then now this is the power rule that we just did a few minutes ago. So I've got my 3, and I'm going to have x to the 5th, 1 up from 4, times 1 over 5. And my final answer will be 3/5 x to the 5th, and you need to put plus c on the end. Right? Oh, looks like I need to turn the page. Next thing is sums and differences. So I know you all remember that if you take the derivative of a sum or a difference, that you can simply take the derivative of each function and add the derivatives together. You can either add or subtract the functions and then take the derivative, or you can take the derivatives and then add and subtract the derivatives. You get the same answer. The same thing is true for antiderivatives. If you've got a sum or a difference of antiderivatives, technically I need brackets right here for my dx. I can do it like this. I can add or subtract the two functions and then take the derivative, or, the antiderivative, or I can take the antiderivative of each one and add or subtract them. We did the same thing with derivatives, and that sounds way worse than it is. It's simply a matter of recognizing that if you want to take the integral of 2x cubed minus 4x plus 5, that you can simply take the antiderivative or integral, I'll keep switching back and forth, of each one of those terms. Now, honestly, we are not going to stop and write this step down each time, but that's what you're doing, taking the antiderivative of each term. So you use your rule on this one, take that 2 down, x to the 4th times 1/4, minus, write that 4 down, x squared times 1/2, plus, write that 5 down, and the derivative of constant is going to be 5x. And we'll just put 1 plus c at the end. You put a plus c on all of them, you just get a bunch of constants and add all this together, and it's just constants. So we're just going to put all of them together here. And then, of course, you want to clean this up a little bit. 1 half x to the 4th minus 2x squared plus 5x plus c. If you want to double check things, take this derivative. Take the derivative of this, and it should take you right back to this. You're certainly welcome to do that anytime you want to make sure that you're doing it right. Okay? Again, we're only going to want to put that 1 plus c on there. There's no reason to put a bunch of plus c's. Okay, let's just crunch through a handful of examples. The integral of 1 dx. This will sometimes just look like this, the integral of dx. Okay? So I'm asking you what function has a derivative of 1? And that answer is x plus c. Okay? If I say the integral of dy, then the answer is not going to be x. The answer is going to be y plus c. I am defining the variable that you're working with. Okay? Another one? Okay? This does not fit into the rules that I've given you. I've not given you any rules for how to take the antiderivative of 1 over something. You have to have x to a power to use the rules that I've given you. So you're going to rewrite pull this up to the top and make it x to the negative 2. You can't use the power rule on this. You have to convert it to this. And then you can use the rule for that. That would be x to the negative 1, and the reciprocal is negative 1. And then clean that answer up just a little bit. Negative 1, x to the negative 1, or maybe even negative 1 over x plus c. That's actually probably the way you want to write your final answer. So when we started derivatives, I talked a lot about changing the way the function looks before you take the derivative. We have the same situation with antiderivative. We want to change it so that it has that look of terms. This term plus this term minus that term, not look of something being multiplied or something being divided. We also want to get rid of that square root and make that an exponent. So this is going to be the integral of 3x minus 2 over x to the 1/2. Some of you like to pull that x up to the top and do distributive property multiplication. I am just as happy doing it with division here. Just remember that the 3x is divided and the 2 is also divided. You're doing both of those things. So my antiderivative is going to be 3x to the 1/2 minus 2x to the negative 1/2. Subtract the powers here, and then take this and just pull it up to the top and make the exponent negative. Okay? And then you follow the power rule that we went over. You don't have any rules to learn. You also got notation to learn today. Write down the 3, skip a little space. X to the, add 1. 1/2 plus 2/2 is 3/2. And then here you do the reciprocal of this, goes here, it's 2/3. 1 over 3/2 is 2/3. Minus 2, you a little bit of space. X to the negative 1/2 plus 1, negative 1/2 plus 2/2 is positive 1/2. Do the reciprocal here, and that's 2 over 1. And don't forget your plus c on the end of that. Okay? So then clean it up a little bit. 2 x to the 3/2 minus 4 x to the 1/2 plus c. If you take the derivative of this, it'll get you back to the original. The derivative of this will give you this. So you can always check the work. All right? Okay, a couple of other really quick things about notation. There's some different ways you're going to see things. If a problem says dy dx equals 3x to the 4, and it tells you to solve for y, what we generally do is called separating the variables. And that means that we want to have anything with a y on one side, anything with an x on the other side. So you basically multiply both sides by dx, leaves you with a dy here, and then 3x to the 4. Now a little disclaimer. Sometimes you can't do this, but that's in higher level classes. Anything that you see in this class, you're going to be able to do this. There are some situations where this is not allowed, but it's outside the scope of this course. But I just want to make sure I said that. All right, once we separate the variables, then they're going to take the antiderivative of both sides. By taking the square root of both sides, that means putting a symbol in there. So I'm going to do it as a separate step here. Normally, you would probably just pop that right into that step above, but just for your notes to see this is a separate step. And then you're going to take the antiderivative of the left side and take the antiderivative of the right side. The antiderivative of 1 dy is y. There's a plus c there. There's going to be a plus c on the other side. We don't need 2 of them. We only need 1. Just 1 plus c, and we usually put it on the right-hand side. Take the antiderivative of this. That's the 3. Leave a little space. X to the 5th. The reciprocal of 5 is 1/5. And put your plus c over on the right-hand side. So our function is 3/5, x to the 5th, plus c. This is a family of functions. This answer here, and also this answer plus 1, this answer minus 6, this answer plus 2/3. In fact, there's an infinite number of answers. So we have to have a plus c there to recognize that. Okay, almost done. Okay, the derivative. of sine x is cosine x. Therefore, the antiderivative of cosine x dx is sine x plus 6. The derivative of cosine x is sine x. Therefore, that's wrong. The derivative of cosine x is negative sine x. Therefore, the antiderivative of negative sine of x gives me cosine of x. Now you can memorize it that way, or you can learn it this way. The derivative of the sine of x is negative cosine of x. And I'll tell you right now that if you had trouble with remembering which the signs were before, this is just going to make it worse. But it is something that you just have to come to grips with. All right? Take a look at page 250 of your textbook for the other one. Okay? All right. And I want to drive home one last time this idea of a family of derivatives, of antiderivatives. If you take a look in your textbook, you'll see some pictures of these graphs that are better than I'm going to be able to help with. If I say the antiderivative of f of x is this, if I tell you this is true, then you know that this is true. That's what you know. If I tell you this, then you know that this has to be true. Okay? And they just differ by a constant. So what that might look like graphically, somewhere in one of the homework assignments, it's going to tell you to graph this. What a weird thing to tell you to graph. Graph an antiderivative. Okay, well, what is the antiderivative of 3? The antiderivative of 3 is 3x. So if I'm telling you to graph this, that's the same thing as telling you to graph that. That means the line y. That means the line y equals 3x. Okay. This is a fairly steep line, goes right through the order. Right there. Y equals 3x. Or y equals 3x minus 1, or 3x minus 2, or 3x plus 3, or 3x plus 5. And the textbook does a nice job. It'll 1 as the rest of light gray. They're all part of the techniques for an infinite number of solutions to the problem. Okay? Again, I suggest you look in the textbook and see what it takes long. So if I tell you to graph this, graph the antiderivative of 3x squared, I am asking you to graph x2. That's what I'm saying. The antiderivative of 3x squared is x2. There was a 3 here, there's a 1/3 here. Those cancel out, and you get x2 plus c. I'm asking you to graph that, with you indicating that you know that it's not just x2, but it's a parallel, if you will. Parallel to an odd word. And my drawing skills are less than magnificent. But the idea is just shifting that graph down so that each one looks exactly alike. Not at all what I have put on the picture. Okay? Alright, that's it. That's all for today. If we have a snow day tomorrow, you can expect to get something from me that will be probably not another video, but notes via your class lecture. Okay.